Hey there, Pythonistas. It's April Fool's Day, April 1st. I remember making another movie on April 1st about Fuller's subconscious demon. If you look back a year, that was about the difference between two rhombic trichondahedron, which I actually am addressing in today's video as well. If you look, I've got the similar code to what we've been doing in the last couple of videos. I've been talking a lot about the jitterbug, which is physically just this transformation. You can see it made out of wood here with rubber joints. And this is kind of a trademark. You'll see almost anyone who's into teaching synergetics is going to, sooner or later, they're going to bring up the jitterbug, which is fine. It's made it into the literature now. You might be thinking, it would have been great if this was just, this is a pretty obscure math. I think you'll agree. It's not in any textbooks, and yet it's simple. It's, a lot of whole number volumes, and you might be thinking, gee, if only this had been developed by somebody really well known. I mean, we've got Kirby here with his sticks, but, if this had only been developed by some great thinker with worldwide recognition, then we wouldn't have this hump to get over. Like, how do we get this stuff to be famous so that it really does get taught? And if only it could have happened like 50 years ago, or maybe 20 years ago, or something in there, somewhere a long time ago, couple, 3 decades. And the thing is, that's all the case. It did happen 50 years ago, and the person who developed it was world famous and has tons of honorary degrees and taught in universities and had architecture awards. I mean, if it was just honorary degrees, okay, maybe that's not so great, but then the Medal of Freedom, and I think honorary degrees are great. You get it's the college pegging the value of its PhD to somebody by giving it to them in an honorary fashion. It's like, you've got to remember this guy and this stuff. This is important. So the generation in which Fuller grew through, I mean, he spanned several generations in his lifetime, I think did a lot of work to make sure we don't forget this stuff. We better take it seriously. And yet, if you look in schools, when did you learn any of this, right? There's been time. I really don't care how old you are by now. You could have been exposed to this. So my sense is we have no public schools anymore. They've all been privatized. The idea of a public school, no, it's more like there's a corporate infrastructure behind a government that buys and sells weapons, and it gets kids to go to school and takes your money for that. But they've all been privatized because none of them teach American literature. None of them, because this is American literature. If you don't know this, you are just too ignorant to ever be president of the United States. Don't even think about it, right? This has to be like grade school knowledge for you. So none of the people currently in office, from my point of view, are in any way qualified, right? It's April Fool's, all right? I mean, they're there. There's nothing we can do about it. But it's kind of funny in my mind. I'm chuckling that we managed to rip ourselves off and not learn some simple geometry. So here we go. I run this thing. Now notice what I've done is I've imported from polys, and this could be fleshed out like I've done in other videos to be a real top-level polyhedron with all kinds of methods. This one can only be scaled, bigger and smaller, and we just pass it directly the number we want to scale volume by. I don't bother to scale the edges and then third power that for the volume impact. That's what we do usually with volume. We double all the edges, we eightfold the volume. We triple all the edges, we raise volume by a factor of 3 to the third power, 27. We don't do that here. Just multiply by scale. So, and I don't have it called jitterbug anymore. I'm calling it the concentric hierarchy. And in the comments, I flag what are the classic jitterbug stops. Like we start at 20, 18.51, 4, and then down to 1. So I've got these stops flagged in the comments so far. Depends what you want to do going forward, if that's good enough. And I don't bother with the coming back out again in a mirror fashion. After you go through 0, you could say this thing turns inside out. After it goes to a tetrahedron, it flips inside out, and whatever that means, right? And then expands kind of in an inside out to what it was. That's the full bow tie. I don't have that here either. But what I do have is another constant called TF, which it looks like TensorFlow, but actually it stands for the T module, the T factor, the T factor. And what that is the scale factor to take a volume 5 rhombic tricontahedron and just make it a tiny bit bigger to the E modules tetrahedron. Let's do a test here. Here's an interesting test. So I'm going to go CH equals concentric hierarchy and start looking at these volumes. And I'll do it real quick simply by doing a for loop. You can go over all the values of a generator by treating it as an iterator, which it is. So CH for poly, I'm just making up a name. I could call it X. For X in CH, the generator object I just created, print volume colon comma X. We'll be simple about it. No fancy formatting. Not going to try to line up the decimal points. And here we go. Not very pretty, actually, because I forgot to say I just want the volume of the polyhedron. It's printing out the name of the object, or actually the representation of the object. Each case it's a polyhedron object, but I just want to see the volume. Thank you very much. So let's do that again properly. And you know why it didn't print anything this time? Because the generator has been exhausted. It went to the end, and it's like a train at the end of the track. It doesn't just back up or anything. Generators don't go backwards. So I need to recreate it once again, fresh from the top, and now we ride our train through all the yield stops and see what we get. And there's our volumes table. And this should start to look somewhat familiar. We've got, at the end here, I've added the might of AAB fame, 2 A's and 1 B, and I've added the just A or B, we could call it, or T, 1/24th, and there are other friends. Now here's the rhombic tricontahedron that's just a little bit bigger, and its radius is not 1. We don't have a unit volume. Actually, its radius is 1. And the radius of the smaller one that's exactly 5, the rhombic tricontahedron that has a volume exactly 5, it has a radius of just a little bit under 1. So it's if you want to shrink wrap a unit radius sphere precisely inside a rhombic tricontahedron, of course you can do that, but its volume in tetravolumes will be slightly bigger than 5. And if you shrink it just a tad more by scale factor, now this is the linear scale factor, 0.9948332, so on, you can get it to be exactly 5, and that's what I've got here. Okay, so that's talked about in other videos. It's interesting how small that difference is. And then volume 6, of course, is our favorite rhombic dodecahedron, space filler, in the CCP packing. And then we've got our old friend, the volume 18.51, which is the icosahedron of jitterbug fame here. So the test I want to do now is to make sure that if let's see, what should we do? What would be fun? Let's make sure that if we take this volume 2.9 icosahedron and subtract and add 24 times the S module. Remember when I said last time, if you brick in the internal icosahedron, the icosa within, if you brick it up with 24 S modules, you should get the volume 4 octahedron. So I want to do a test of that, and it'll have some floating point error probably, and that's why in other videos I go out to really extended precision, maybe 200 decimal places or so on. But in this case, we'll just test. So icosahedron within plus 24 S modules, and there we're pretty close. That would be 4 if I went out to extended precision. All right, fun to play around with this, and make sure you take advantage now of the new polyhedron class as you wish. You could start putting names of the polyhedrons in there, how many vertices, edges, and faces, and eventually we can get into rendering. And before you know it, you've got a full concentric hierarchy rotating and dancing on your screen in a hypertoon. All right, happy April Fool's Day.